Okay, so the section is over. We are now going to solve the exercises, and this is the first one. It is in fact a characterization of infinite sets. That means it gives us a necessary and sufficient condition for a set to be infinite. So what it says is this: X is a set, X is infinite. We have to show that X is infinite if and only if we can find a proper subset Y of X which has the same cardinality as X. That means if and only if such a proper subset can be found so that there is a bijection between X and Y. This is what we have to show. So let us now see how we can solve this. So one half of this claim comes from a property of finite sets that we have already seen and proved, and that is this proposition three, 6, 14 part C implies that if we have a subset Y of X which is a proper subset. We need not explicitly mention again that it's a proper subset because this is the symbol for proper subset. Y is a subset of X and it's not equal to X. Okay, if we find such a subset, if we have a subset which has the same cardinality as X, then X is infinite. But exactly how? And in fact, what was this proposition? Let's just recall the statement of this part. What the statement says, we only need a portion of the statement, in fact only a portion of the part C for this conclusion. So this it said this: if X is a finite set and Y is a subset of X, then Y is finite and the cardinality of Y, different texts denote the cardinality of a set using different symbols. This is the symbol we are using in this text. The cardinality of Y is less than or equal to the cardinality of X. But it has something else. In fact, that's what we are using here. In particular, if Y is a proper subset of X, then the cardinality of Y is strictly less than the cardinality of X. So how are we getting this conclusion? The thing here is this. See, we want to conclude that X is infinite. Say it is not, that means suppose it's finite. Then we can use this result, that according to this result then the cardinality of y should be less than the cardinality of x. But that directly contradicts this hypothesis that they in fact have the same cardinality, and that's why our supposition that x is finite would be wrong, and this is why x is infinite. Okay, so this half of our if and only if claim is over. Now we go to the other half. Conversely, let x be infinite. Now we need to find a proper subset y of x which will have the same cardinality as x. That means for which there would be a bijection between that set, that proper subset, and x. So we need to find that y. And for that we are going to now claim something else which would be useful. We claim that our original infinite set x has a subset whose cardinality is n for each natural number n. That means we are claiming that whatever natural number n we choose, we will find a finite subset of x having that n as its cardinality. And this we are now going to prove. We need to prove this claim. We have made this claim. That does not mean it should necessarily be true. We need to prove this. So we are going to prove this by induction. We prove this by induction on n, and you can of course see it's extremely straightforward. The claim is true for n equal to 0 since the empty set is of course a subset of x whose cardinality is 0. In fact, this is the only set having 0 cardinality. Let us suppose that there is a subset so now we are going to write the induction hypothesis. That means let there be a subset of x whose cardinality is n, where n is some arbitrary but fixed natural number. Such that this is equal to n. Where n is some natural number. Okay, now this is where we are now going to use the hypothesis that x is actually an infinite set, since x is infinite A is bound to be a proper subset of X. Keep in mind that infinite by definition means not finite. So X cannot possibly be equal to this finite set A, because it is A is finite because its cardinality is a natural number. Okay, so A has to be a proper subset of X, and that's why we can choose an element X in X which is not in A. That means X lies in this set difference. Then by proposition, again proposition 3, 6, 14, but this time part A. The union of A and this singleton set is of course the subset of X, such that its cardinality is one more than the cardinality of A. In fact, this is where we are using this proposition. So, having assumed that there is a subset of cardinality n, we have produced a subset of cardinality n plus 1. The claim is thus established by induction. Okay, so now we are going to choose one subset of X for each cardinality. Because this is an infinite number of choices, we actually need the axiom of choice, which we have so far not obtained, but I think we discussed this before also. Anyway, we choose a subset an in order to show that this has cardinality n. We are using the suffix n. Of cardinality n for each, actually let's consider positive integers n or positive natural numbers, because we are now going to take the union of all these an's, and the empty set will not play any role. But if you want, you can just write natural numbers also for each positive integer n. We are using the axiom of choice. Here, for which we have to see this section 8, I mean in the 4th section of this chapter itself we will get this, but we have to wait. Now, consider the union consider the union B, which is the union of all these ANs. Okay, now we are doing many things here. Okay, let's see if whatever we have done is logical or not. We completed the proof of that claim, and due to that claim, for each n, such a subset of cardinality n can be found. So if you look at the situation here, you get classes of subsets of X. These are classes of subsets of X categorized according to their cardinality. This class has subsets of cardinality 0. Well, of course, there is only one element in this class. This class has subsets of X of cardinality 1, and there are many elements in this class which themselves are of course sets, then 2, 3 and so on. It's like having infinitely many bags or containers. Each container is non-empty, and from these containers, this first container of course is being ignored here. Starting from this container, we are choosing one element from each container. So this is A1, this is A2, this is A3. Because it's a sort of arbitrary choice, we are not giving any specific rules for how we should choose one element from each class or each container or each bag. And there are infinitely many containers, so we need the axiom of choice here. It seems like something that can be done, and in fact when we introduce the axiom of choice into our set theory, we will see that it is in fact an axiom, and we are going to assume that it is true. Why we need to make this extra assumption and include it in our set theory? It's because this fact cannot be proved by the other axioms that we have seen so far. However, in some situations it becomes absolutely necessary. Here, however, it does not feel like that. I mean, we can of course choose one set of for each cardinality, that we can do, but in some situations where we need to be more specific, then there is no other way to make such choices other than using the axiom of choice to make things absolutely rigorous. However, we have done it here, and now we move on. Okay, so what we now did with these sets is that we have taken their union. Because each an was originally a subset of X, naturally this B being their union is also a subset of X. Note that B is a subset of X. Also, B is infinite. Okay, but why is that so? Why is B infinite? And this part can be answered again by that part C of proposition 3614 in this way. Say B is not, I mean, we of course feel that B should be infinite because we are taking the union of larger and larger sets, but we have to rigorously justify it also. No? Suppose B is finite. If B is finite, then it should have some cardinality which is a natural number. Let that cardinality be M. Okay, it will be some natural number. But what is the cardinality of A M plus 1? According to how we have made these choices for these subsets, this cardinality is M plus 1. But clearly, because B is the union of all these AIs, AM plus 1 is a subset of B. Now, because we have supposed that B is a finite set by that part C of that proposition, we should get this. Which, however, is clearly not true. So there we have got a contradiction. That is why B cannot be finite. It has to be infinite. But something else about B is also true. You see that B is in fact a union of not just arbitrary sets but finite sets, and finite sets by definition are countable. And we have already seen one proposition or result in this section which says that a countable union of countable sets is countable. Okay. In fact, precisely what is that result? That is in fact not okay. That in fact is a result, but it's not exactly here in the section. In the section among the results that we have seen so far, we don't see that thing, but it is one exercise that is going to come. Okay, it's exercise 819. Since each AN means the ANs that we are considering here in this union, since each AN is finite and hence countable, exercise 819 implies that B is also countable. Oh, okay, I cannot write countable. No, this is, by countable we mean that it has a bijection with the set of natural numbers. I should write at most countable, yes, and hence at most countable exercise 819 implies that B is at most countable. At most countable means either the set is finite or it is countable. So you understand what this exercise statement is. It asks us to show that if we are given a countable union of at most countable sets, that means the number of sets involved in that union is countable, like what we have here, then the union is also at most countable. But you combine this at most countability of B with its infiniteness, then you get the conclusion that B is actually countable. Since B is in fact infinite, it should thus be countable. Okay, now because B has been proved to be countable, there exists a bijection between B and N. At least one bijection, but we can choose one. choose a bijection f from the set of natural numbers onto B. Okay, now we are ready to define that bijection which we want, and in fact we are now ready to say what that y is, that proper subset we are seeking. Now define the function f from, perhaps I should instead of cramming things here, I should write like this: f from x into x minus, we already have f, so I have to give it some other name, g from x to x minus f of 1 by what? What is the rule of this function? By this rule. G of x is defined to be equal to f of n plus 1 if x is equal to f of n for some natural number n, else it is x itself, otherwise. Okay, now at first glance all of these things seem extremely complicated. So after defining this, actually this will be that bijection that we are seeking, and the proper subset of x that we want here is this y. This clearly is a proper subset of x. Why? Because it does not contain f of 1. By the way, is f of 1 an element of x? Yes, it is. Why? Because f of 1 is an element of b and b is a subset of x. So after all, f of 1 is in x. So we are removing this f of 1 from x and we are setting up a function between that proper subset and x, and this is the function. Now let us see what the function actually does. Let me write the concluding thing here and then we will discuss. One can show that G is a well-defined bijection, and this is where the solution ends. Clearly, I am asking you to show this. Okay, this is left to you. But let us now see what is actually happening here. Okay, and let me do it here on this side. Do you see what we have done with B? In fact, we have shown that because we have proved that B is countable, we have just shown that X has a countable subset B, and we are using this set B to set up this function in this way. Okay, so this is our X and this is again x, another copy of x. Inside x we have b. Now because we originally had this bijection f from n to b, so all the elements of b due to the presence of this bijection can be listed. That is, we have f of 1, f of 2, well okay, f of 0 would come first, no? Oh, so then I may need to change this a little bit. I am saying f of 1, let me make it f of 0. That's because we are talking about natural numbers, no? F of 1, f of 2 and so on. It goes like this, it does not end. Here also we have f of 0, f of 1, f of 2 and so on. It goes like this. And whatever else we may have in x, I am saying may have in x because it may turn out that b itself is x. That is also a possibility. Otherwise there would be elements in x outside b. Something like this. Say we have an element here, some x. Okay, now what this function g is doing is this. If it turns out that the input x falls inside b, then it is equal to f of n for some natural number n, and because this f is a bijection, there will be precisely one n for which this will happen. We cannot have x equal to f of n and then x is also equal to f of m for some m not equal to n. That will not happen because the function is one to one, it's injective. So we have x here somewhere. Say we have f of n here and f of n plus 1, and it of course does not stop. It goes on forever. So if our x is this thing, then g maps that onto this, the next one. Okay. If our x is, for example, f of 0, in order to be specific, say x is f of 0, then that gets mapped onto f of 1. F of 1 gets mapped onto f of 2, f of 2 gets mapped onto f of 3 and so on. If we have something else, x, which is not in b, being in b means of course having this condition, but if that is not the case, if we have x outside b, then we map x onto itself, and this sets up a bijection between x and x from which f of 0 has been removed, and you can see why. I mean, in this diagram you can see why, and using this diagram you should be able to write a rigorous proof. Keep in mind, we cannot just simply leave things like this. I am leaving it here only for you to fill in this gap. Okay, so you need to show many things here. You need to, that's why I deliberately mentioned well defined. Keep in mind, whenever we are defining a function, we have to always show that it's actually a function, it's a well defined function. So you need to show, in order to prove that it is well defined, that g actually maps x onto this, into this set, and then you have to prove that for every input there is a unique output. That proves that g is well defined. Then you have to prove it's injective and surjective. Then only after that only we can claim that it's a bijection, and thus infiniteness of x has resulted in the existence of such a proper subset of x with which x has a bijection. That means they have the same cardinality, and this is where the solution actually ends, provided you manage to show all these things. Now we solve the next one. And the next one is this: we have to prove the well ordering principle, which we mentioned. This is not very long. Prove proposition eight one four, and hint is given. The hint is a little long. You can either use induction or use the principle of infinite descent. This is also something we saw back in the section on induction. Principle of infinite descent which is exercise 442, or use the least upper bound property least upper bound or greatest lower bound. Properties. So many ways to approach. Least upper bound. Okay, principle the author has written. Which is theorem Theorem 559. But that's not all. We have to also answer these things. Does the well ordering principle work if we replace the natural numbers by the integers? By the integers. What if we replace the natural numbers by the positive rationals? Explain. Oh, it took up the whole space. Now before I do anything else, let me refill. The statement of the exercise is long due to this elaborate hint, but the solution itself is not very long. Okay. So we have seen what we have to prove. We have to first of all prove this proposition, which is the well ordering principle. The statement is of course that if we choose a non-empty subset of the set of natural numbers, then there exists a unique smallest element. And then of course we have to answer these two things, that if in place of the set of natural numbers we have the set of integers, is it still true? What if we instead have the set of positive rational numbers? Then what? Okay, so let's now see the solution. Actually we should just start writing the solution, but because we do not see the statement in front of our eyes, so let me just again write what we are given. Let x be a non-empty subset of the set of natural numbers. We can prove the uniqueness of the smallest element later, which is in fact not something very difficult also. There is just one line we have to write, but first of all we have to show its existence. Suppose it does not exist for x. Suppose x has no smallest element. Okay, but the set of natural numbers itself has a smallest element, which is of course 0, since 0 is the smallest element of n, we must have 0 not in x. Why? That's clear, because if 0 is there in x, then 0 is bound to be the smallest element of x. Why? Because if x has nothing other than 0, then of course it's trivially the smallest element, because it's the only element. But if you have something else in x, then that something is strictly greater than 0. Then also 0 is the smallest element. So that is why 0 cannot belong to x due to this supposition. We are now going to prove by induction that actually nothing is in x. In fact, strong induction. Let m be not in x for all natural numbers m less than or equal to n, where n is some natural number. That means n is some arbitrary but fixed natural number, the way we make induction hypothesis in strong induction. Then n plus 1 also does not belong to X, as otherwise n plus 1 would be the smallest element of X. Why? Because you see, according to this assumption, this our induction hypothesis, none of these natural numbers belongs to X. Now, in this situation, if it happens, otherwise means n plus 1, say n plus 1 is in X, then n plus 1 has to be the smallest element. Why? Because you take any element in X, this any element X cannot be from among these m's, because according to our hypothesis, none of those m's belongs to X. So that means X is not less than or equal to n. That means X is strictly greater than n, and because X is strictly greater than n and we are talking about natural numbers, so one of the properties of natural numbers is this, that this inequality means that X is greater than or equal to n plus 1, and that is why n plus 1 would then be the smallest element of X, which according to our supposition is not there. Okay, it does not exist. So n plus 1 also will not be in X. So what have we shown? Now by the principle of strong induction, we can say that actually no natural number belongs to X. So by the principle of strong induction, no natural number is in X as an element. Okay, so X has no natural number, but X in fact is a subset of the set of natural numbers. So combining these two things, the only conclusion is that X is empty, and that is a contradiction. Combined with this fact, we then must conclude that X is empty. This is a contradiction to the hypothesis that X is non-empty, and so our supposition means the original initial supposition. If you want, you can write, so our initial supposition is wrong, that is X has a smallest element. We are not writing that. Now comes the uniqueness of that smallest element, which of course is just a consequence of the anti-symmetry of the order relation that we have in N, and we just simply write that. The uniqueness of the smallest element of X follows This way also we can write follows from the antisymmetry or anti-symmetry if you are from that part of the order relation on N. How? Say you have two smallest elements A and B in X. What is the condition that A is the smallest element of X? Namely that A is less than or equal to every element of X. In particular, A is less than or equal to B. But if you do that same thing with B, switching the roles of A and B, then you also get this. Then antisymmetry tells us that then A must be equal to B. So that's how the uniqueness comes. And now the final part of the solution. What happens if we have the set of integers in place of the set of natural numbers? Then the well-ordering principle fails. The principle that means the well-ordering principle fails in the system of integers. The non-empty subset which is Z itself of this has no smallest element. Having recognized that we are just simply using the fact that if we move to the left of the number line, then we have used the fact that D is not bounded on that side, okay, by anything. But then the author then gives us another challenge. Okay, so you replace the set by the set of positive rational numbers. Now there is a bound. Okay, then what can we do? The principle still I should not write still, is not true in the system of positive rational. I am not exactly sure, or I don't remember if this is the symbol we are using in this book, but you understand that by this I mean the set of positive rational numbers. This either the non-empty subset has no smallest element. Now if you want to be absolutely rigorous and not just simply take these things as facts, we of course know they are, but if you really want to prove these also, that okay, say someone asks you, why is there no smallest element of this subset? You then have to actually demonstrate why there is no smallest element. And for that, we can of course use the Archimedean principle. So in brackets I write to show that none of the two subsets above, that means this one and this one, has a smallest element, use the Archimedean property or principle. But how are we property? Use the Archimedean property. Archimedean, have I got the correct spelling? Yes. And it is, in fact, if you are wondering where this thing is, this is corollary five, 4, 30. Okay, so that completes the solution, and let's just stop things here. It's, I think that at least I feel like this, that we should solve only 2 or 3 problems, but understand the solutions properly instead of solving a lot of the problems and rush through the solutions. Okay, so that's just it for tonight. If you want to say something, you can write in the comment section below, or you can mail me. My address will be there in the description. You already probably know. And this, so today is what? Today is Sunday. So the next upload is on Tuesday. And on Tuesday, we are going back to graph theory, where we are, I think, right now going through that section which is somehow linking notions of graph theory with linear algebra. That is, we have so far seen vertex space, edge space, and now we are going to see some other things. So with that, I wrap things up. So see you next Tuesday with graph theory. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.